Oh, yes, it's Renit's birthday. Renit, I'm so proud of you. You, besides the fact that you're endearing and you have brains and you have these great students, I mean, you've been really wonderful. I'm so proud of you. And the students are here and they're going to be great too. So thank you. So this talk is about a model of consciousness that Lenore and I defined. We call it the conscious Turing machine. It's not a Turing machine. We call it a Turing machine mainly because Turing created this beautiful machine, very, very simple, that for deciding what's computable. And our conscious Turing machine is defined in order to understand consciousness. It's not computability, it's consciousness. There is an application to AGI, we hope, because the CTM is a federation of 10 million AIs. 10 million, why 10 million? Because our brain has 10 million cortical columns. And we're making use of, throughout this talk, when I talk about a person or the infant or whatever, I'm assuming that they have a CTM brain. Because if they don't, it doesn't matter. This is a formal model, and the theorems and the statements are all about a robot or a person with that formal model. My own interest in consciousness began when I was in second grade. I was a very dumb kid, and my second grade teacher, told my mother that I might be able to get through high school, but don't expect I can get to college. I asked my dad what I should do about it, how to remember stuff. I couldn't even keep stuff in my head, how to remember stuff, and he hemmed and hawed, but eventually he had this great idea. He said, if you understand what's in your head, you can be smart. And I thought, what a great idea. So that was second grade. I do remember in fourth grade walking around in the garden trying to introspect what's in my head. That doesn't work. Try as I might. It felt like there's a homunculus in my head looking out through my eyes, and in order to understand what's in my head, I'll have to understand the brain of the homunculus. Well, clearly, fourth grader understands that that doesn't work. I did manage to get to MIT, and there I took a course on Freud with Richard Schoenwald. That was my sophomore year. And my junior year, he told me, go introduce yourself to this great neuroscientist who has come here, Dr. Warren S. McCulloch. McCulloch and Pitts had defined the formal neuron, and they were the first to prove that you can build a Turing machine out of neurons. We of course know that, but they were the ones that first proved it. McCulloch, Warren, to me, was a wonderful person, a wonderful mentor. Fantastic. Anything I wanted to do, he encouraged. He was positive, except for one thing. A few months after I started working with Warren, I told him, you know what I really want to do? I want to understand consciousness. And for the first and only time in his life, he told me, you will not work on consciousness. You know, that was 1958. And at that time, it was absolutely verboten to work in consciousness. Later on, it became 1990, roughly. You have Francis Crick. His book comes out, The Astonishing Hypothesis, that namely everything we see and feel and, you know, the pain we have when we stub our toe, all of that can be completely follows from the mechanism in the brain. And that's the astonishing hypothesis. That's what McCulloch assumed and everyone around him. And that's where I am today, too. In 2005, Lenore told me, look, you couldn't work on consciousness, but now you can. It's become acceptable. Not to everyone, of course, but there was at least a group of scientists who were doing it. That was wonderful. And in fact, everything I talk about here is together with Lenore. She's an equal partner in this. Lenore told me, 2005, to read Bernard Barr's In the Theater of Consciousness. And Barr's says that what's in your head is a theater. Think of it as a stage, a theater with lots of audience members looking up at what's going on the stage. And that is what you're conscious of, is what's going on the stage. That was Barr's model. And that's what the fourth grader was looking for. Exactly that. I'm so pleased that I can explain it to the fourth grader now. There is a Barr's model and the conscious Turing machine on the right. Just a few things. Okay, that's all right. So they're somewhat different. For example, in Barr's model, you have the input coming in on the left to the stage and then going out on the right. And the conscious stuff is here between the input and the stage. And down here are the long-term memory processors. In our short-term, so our model is different. We are making use of the fact that we know stuff about the brain now. And for example, we know that the input doesn't go to short-term memory. It goes down to some processors that are especially designed that are special, that, you know, that look at what's coming down in the input and transform that into a chunk. And that chunk is what gets up to short-term memory is always only chunks. And what's up there in short-term memory is a broadcaster, really. It's a buffer. It's not a processor even. It's just a broadcasting station. And what's up there gets broadcasted to all of the processors down in long-term memory. Consciousness, the conscious attention is defined to be the reception by all these processors, all long-term memory processors, of what's broadcast from short-term memory. So of course, if any set of processors is responsible for what's going on there, that set of processors will know from the broadcast what's going on. And so similarly, there are some processors that receive chunks and send to the arms and legs instructions what to do. A bunch of, let me just mention central executive. In Barr's model, there is a central executive that sort of, it's like the head of an orchestra, the president, the governor. Every large group seems to have a governor of some sort. Every theater model of consciousness has a central executive. Ours does not. Ours is the only one that does not. The decisions, what to do. Yes, Funda, go ahead.
I was going to put it in slideshow.
No, I don't want it in slideshow anymore. Yeah. Thank you. Is it big enough that you can see? That doesn't matter. Not big enough. So example of our theater model. So let me explain to you how this theater model works. In the CTM, there is one person up on the stage. It's not a whole play going on. There's just one person on the stage. That person is given a script, and that script is broadcast from short-term memory. That's it. Short-term memory is just that broadcasting station. So here's how it works. An example of our theater model. What's her name? You've been to a party. You see somebody you know, you're talking to them, but for the life of you, you can't remember their name. We've all had that experience. And maybe while you're there, you might have this is broadcast, right? There's some processor in this CTM that's really embarrassed, and it puts a great weight on getting up on the stage. It gets up there and says, I'm embarrassed. What's her name? And that's broadcast. And then later, maybe some processor says, oh, I remember. I met her at the Simons Institute. And then another, that's broadcast. And then another processor comes up and says, her name begins with T. And that's broadcast. And in my experience, the name does not come up. It doesn't come up until I'm driving home and I'm not thinking about it anymore. And bam, from nowhere, the name pops up. That's interesting because it's useless by that time, but also because it shows you that some processor in there has been thinking about it. This thinking has been going on and you were not at all aware of it. You're aware, you're conscious of only what's broadcast from the stage. You are not conscious of what's going on in these unconscious processors. Okay, so what are we doing? Barr's theater model has problems. For example, Barr says that the audience members get together to decide what information should get up on the stage. But he doesn't say how they get together or what they do, how they decide. We will do that. Barr creates an informal model. It's not really, there's a picture there, but it's not really a formal model. When a task has to be performed, the director has to choose a processor to do that. So everyone has this executive director who's supposed to choose the processor to do that. You know, you might want to have some processor specialized to remember names. I really should get one of those. Okay, right. So I really should do that. Where am I? Test to be performed. So the director, the director has to know which processors have time to do that. What are the abilities of the processor? Some processors have some abilities, some have other abilities. How can the director know all of this to decide who to give the task to? So in the CTM, the way it's decided is when there's a task to be performed, everybody does it. It's broadcast. This has to be done, and everybody does it to the extent that they have the ability, the algorithms, the knowledge, the time to do it, because they may have other stuff to do. They all do it. And then the one that gets up on the stage may not be the best, probably not the worst, somewhere in the middle. Every processor looks up and sees. So when that processor gets up on the stage and broadcasts what it's doing, then half the processors can drop out. Half the processors will see that they're not as good. Other half sees that they're even better. Or if a processor doesn't know, it flips a coin to decide. Okay, so
Communication. How do they?
all the communication is by getting up on the stage and broadcasting. So in the infant, okay, we'll get to that in a second. In the infant, there's no other way for two processors to talk except by getting up on the stage and broadcasting. If in the CTM, if there's a problem, a question, for example, you get up on the stage, you broadcast. If some processor has an answer, it gets up on the stage and it broadcasts it. And if you agree that that's a good answer and you get up on the stage and broadcast it, then a link forms, a two-way link between the processor that had the question, the processor that answered it. That's the only way in which links are created. Okay, so definition of the CTM. First of all, time is measured in ticks. 10 ticks per second, that's the alpha rhythm of the brain. That's the rhythm of the brain when you're meditating or when you're in a good mood. out 10 ticks per second. When you're thinking really hard about something, then the fastest rhythm is that of the gamma rhythm, 100 ticks per second. In the CTM is born at time 0, it dies at a certain time, capital T, and the clock runs at 10 ticks per second, just like the alpha rhythm. Here's the so what I wanted to do is show you, I'll show you roughly how the CTM is defined. CTM is a 7-tuple. Isn't that the way mathematicians like to talk about it? It's the 7-tuple. It has STM, that's the stage, LTM, the processors at the bottom, an up tree, which is a competition that's run among the processors to decide what will get up to the stage. It's a binary competition. That's the up tree. And because it's binary and there are 10 to the 7 processors, it's log to the base 2. It's about 23 steps for information down in the long-term memory processors to get up to the stage. And then there's a broadcast. Whatever's on the stage gets broadcast. That takes just 1 step. Bam, that's fast. This, by the way, is roughly what the neuroscientists tell us is going on, in that they also see that stuff in the unconscious stuff takes time to get up there to consciousness. Decisions are made before you even know that you've made them. Okay, so we have STM, LTM, up tree, down tree. Links are channels for transmitting information. And like I said, the link between 2 processors is not created at the beginning. It's created only when it's needed, and then it's there permanently. Why is that? And so this is an example of how the model is created. There are 10 to the 7 processors. That corresponds to the number of cortical columns in the brain. 10 to the 7, 10 million cortical columns. Each cortical column is a processor with about 1,000 neurons. That's the 10 to the 10th neurons that you have there. Am I done already?
Maybe another minute.
Okay, so so let me just mention that there is this formal definition of the conscious Turing machine, that the processors themselves, there's 3 kinds. They're the processors that receive input and transform what's there into a chunk, and they're the ones that send output. And then there are processors there that are gauges. You have lots and lots of gauges. So let me just mention that what every processor does is it has some information. It wants to send up to the stage. It puts that information into a chunk, and all that ever gets up to the stage is a chunk. So definition of a chunk. So George Miller wrote, sort of informally defined a chunk. He's the one that said, you have 7 plus or minus 2 chunks in consciousness at any moment in time. We have only one chunk. In part, it's great because we can show that you can do everything you want to do with just 1 chunk. I never could understand how you could get by with just 7. A chunk was never formally defined. A chunk is a digit, a word, a phrase. We define a chunk formally. So a chunk is a 6-tuple. And this is what processors put into the competition. An address for the chunk, the address, the processor that puts the chunk, at every tick, every processor puts a chunk into the competition. Bam. And then it starts its way up, and then at the next tick, every processor is putting a chunk into the competition. That chunk consists of a processor name, the address of the processor, the time at which that chunk got produced, the gist, which is like the information that processor wants to send up to the stage, the weight, which is something which says how important it thinks that information is. That weight is any integer can be a weight. Any real number can be a weight, and the weight can be positive or negative. Negative, you pain. Positive, pleasure. Curiosity could be either one. There are two additional things: intensity and mood. Definition of a chunk. So is the language that processors use to talk with each other. I'll give one last example of how this works. You'll get the idea from this. Let's look at the infant when it's born. Infant, when it's born, has all these processors. There are no two processors are linked. No processors know what's going on, nothing. The infant is born, the processors don't know anything. The visual processor sees a gray blob at best, and everything has a weight of plus or minus 1. Nothing really useful. Except at some point, some processor, a gauge, which is measuring oxygen, begins to say, hey, I need oxygen. And it keeps on increasing the magnitude of its weight until it gets up there. If all the processors have a weight of 1, more or less, then there are 10,000 processors. To be sure of getting up there, it's got to get a weight of about 10 to the 7. It's got to, and the weight goes up 1, 2, 4, 8, 16. By the 10 to the 7th, there's 50% chance of getting in. So there's the infant. There's one processor that measures oxygen, that really sets its weight up high, and basically this is like, think of it as a scream from the stage. I need oxygen, and then the scream gets louder. I need oxygen, and the processors, they don't know what to do. They just, the thing's just been born. The processors have no idea what's going on. All they know is that they got to do something. And so the arms will start moving, the legs will start flailing, the baby, the infant will pee and poo. This is all, by the way, really what happens. And at some point, that the voice comes in, and that infant either screams or cries, and then the oxygen comes in. So now, for the first time, there is a word, a brainish word comes into use. That brainish word says, here, this processor, that's the word for oxygen. So that's what worked for this processor. For this processor, what worked is to cry. And now, next time it needs something, it'll think of crying, and eventually it learns that crying and screaming gets it everything it needs. And that's how the infant works. Let's see. I think, yeah, I'm out of time. Okay, so I'm out of time. So I didn't tell you how the competition worked, of course, but
Well, I'm sure a lot of people will love to talk to you during the break about how the rest of it goes. So thank you so much for this wonderful talk.